Good morning. We will be starting off the session in another 4 to 5 minutes. Let more participants also join. Well, good morning. Starting the day with a quote, what new technology does is creating new opportunities to do a job that customers want done by Tim O'Reilly. Well, a very good morning and a warm welcome to all the participants who have joined with us on the second day of the online faculty development program on innovation in recent trends and research applications on computing and informatics, SSET 2023. The speaker whom we have with us today is Dr. Shunirmal Khatua, who will be delivering his lecture on cloud computing. Dr. Khatua is presently working as Assistant Professor in Computer Science and Engineering Department at University of Calcutta. Previously, he has won Visvesvaraya Young Faculty Award from DIC, Government of India, in 2018. He has also been involved in several research projects, some of them which includes object identification through syntactic as well as semantic interpretation from a given scenario funded by DRDO, and GPU cluster-based computing, SAP DRS2 funded by UGC. He has also several publications in international journals and conferences, and his research interests include distributed and cloud computing, wireless and mobile computing, big data, Internet of Things, and 5G. Sir, the platform is all yours. You may now start the session.
Thank you. Am I audible?
Yes, sir, you are audible.
Thank you, Amrita, for your nice introduction. And I think today is day two. So already the faculties are got what is going on in SUSET 2023. My topic is basically in the cloud domain. So, so let me share my screen first. So is my presentation visible?
Yes, sir, the presentation is visible.
Okay. So a very good morning to all of you. Uh, Today, the next 1.5 hours, I will cover mainly three important parts. The first thing is distributed computing platform that are heavily used today because rarely we use the centralized systems to run any project or any kind of computational or storage job. Then I will discuss about this big data kind of big data analytics using this distributed computing platform and cloud computing that is called large scale computing. So in summary, if you summarize the topics to be discussed today, the first thing that I already told you, brief introduction to distributed computing platform in general. Then I will concentrate on the platform used for big data analytics. So today you know about lots of machine learning algorithms that require to analyze a large amount of data. So how you can store this large volume of data and perform parallel analysis on those data. So various platforms are available for that I will discuss. Followed by I will discuss about the cloud computing part. So this cloud mainly for computation, even though the cloud can also be used for large scale storage. So I will concentrate in the third part for the computation aspect. For large scale computation, what are the platforms available and how we can use it. And finally, I will discuss about some of my research, basically my team's research that work on the resource scheduling strategies, efficient resource scheduling strategies for distributed computing platforms. How we can create specifically on energy efficiency. How we can run the jobs with minimal number of carbon footprint or minimum number of energy requirement for that. So let us start with first what we mean by computing platform. So already we know about our centralized environment. So this one is a centralized platform. You can see here. So here, so in centralized system you can see in centralized system you can see that all the tasks of large computation run in a single computer. So obviously when the number of subtasks, the number of sub-process increase, become some billions or millions kind of things. So there is overloaded in a single computer system. So then what we do, we increase its performance. So instead of standard desktop computer, we go for mainframe, mini, and today supercomputer also we are using. So this approach of dealing with the huge resource requirement for large scale computations is called vertical scaling. So we scale vertically. We don't add extra resource, but the same resource, its capacity, its capability increased. We increase its RAM, we increase its capacity and output. But nowadays, in distributed computing environment, what we do that all those subtasks, large computational job, that the large computational job are distributed across multiple commodity hardware. So we don't scale vertically, but here we scale it horizontally. So instead of a single computer, large scale single computer, multiple low-end computers use these multiple low-end computers. For example, this is one computer, this is another, and distribute the subsystem. Some of the processes will be running in computer one, the remaining will be running in another computer, and then they will perform some interprocess communication. So in general, a distributed computing environment can be categorized based on these 4 points. So you first thing you need to do is you have to divide your process into multiple sub-processes using either multiprocessing or multi-threading, and then distribute this multiple process across multiple. Some of the processes will be running in node 1, some of the processes will be running in another computer. And then perform some inter-process communication among themselves. Because some of the subtasks still need to access the service provided by the others. So for this inter-process communication, we provide the remote procedure call. So this process we can call the procedure running in another computer. And usually these remote procedure calls are called the web services. And most specifically we are calling about them the microservices. So microservices are basically independent. We are independent of each other because all the microservices are running in disjoint address space. So for example, one microservice running here is not dependent on the other services running in other computers. Now we need a service orchestration. To solve a particular problem, all the microservices has to be orchestrated. They have to be run in a particular chronological order to solve a collective goal, to solve a single problem. So in general, a distributed computing platform can be classified by multiple process, inter-process communication, disjoint address space. That means there should be loosely coupling. They should not depend on each other. Each of the services run by independent authority. And then collectively, even though those services are run by different authorities, by a proper service orchestration, they can solve a single problem. So collectively, they can solve a goal. So this kind of platform basically solve a large problem with multiple nodes horizontally. So in that, the main thing is that there are independent computers, but that acts as a coherent system. Coherent means as if all the nodes belong to me. So basically, the platform provided as a data center kind of thing. So this one is in the picture of a data center. So what they do, they basically have some racks. So for example, in a data center, this is one rack. In each of the racks, they have some blade server. So you can see this is one blade server. This is another blade server. So lots of blade servers are jacked into the racks of that. Now on top of the rack, there is a switch. These are called the rack mounted switch. So as each rack is a local area network. They provide a very high-speed connectivity, high-speed data transfer among the nodes within the rack itself. And the multiple racks are connected by some aggregation switch. So for example, you can see there is a switch, there is another switch, there is another switch. So all the switches are connected to some aggregation switch of that. So that all the racks are connected by themselves. So we are forming a huge amount of nodes. So now you are giving a large scale storage or large scale computation. You have to divide into multiple processes. Those processes you have to distribute across multiple nodes of the racks. And they will solve a problem collectively. And we can provide. So this is basically a horizontal scaling kind of things. Instead of a single supercomputer, so we can have a large number of low-end computers forming a distributed computing platform. So that will provide you a benefit of cost versus performance. So we will get the same performance at lower cost compared to a large-scale supercomputer environment. So now, if you see in distributed computing platform, if we go to implementation wise, so basically we can see that lots of computers are connected by some local area network. Each of them have their own kernel, OS kernel, and some network operating services. So by this network operating services, any of the nodes can log into the others and can have access to the resources since they have some network OS involved there. Now on top of the collection of nodes, you have to install some middlewares. This middleware basically provides you 1 minute. And that is the second half here. Now I'm going to classmate because so the first thing from the software point of view, you need to install the middleware service across multiple nodes of the data center. And this middleware service will provide you the services so that you can run your distributed application. So as a user, you have to write your distributed application and install middleware services, and that's all to you. So all the complexity of the distributed computing will be handled by this middleware. Once you have the middleware, just use the services provided by the middleware and write your distributed applications. Yes. So from that point of view, my discussion is that the various middlewares provided for large-scale storage, the various middleware provided for large-scale analytics, and various middlewares provided for large-scale computation. That I will discuss one by one. So first I will discuss the middleware that is used for large-scale storage. So let me discuss about what is the middleware available for large-scale storage. So lots of middlewares are available here, but I will discuss about Hadoop distributed file system, which is freely available. So you can also download and install in your lab. And also you do not need this kind of data center. You have your lab 1 in your college, you have your, suppose this is lab 1, this is lab 2. Each of the lab there are some computers. You choose those computers and you will install the Hadoop across the nodes in the lab. And in your college, the two labs are connected by some switch. So there is automatically aggregation done there. So you do not need data center for installing this Hadoop distributed file system. Just choose some of the lab with some of the computers of each of the lab and install the various softwares available in HDFS. So HDFS mainly provides two kinds of softwares. The first software is called the data node software. So first install the data node in some of the nodes here. Data node software will use the disk available in that computer in your lab and you will install the blocks of the file, because your large file has huge number of blocks. Each of the blocks generally has a multiple of 64 MB kind of storage. So that these blocks, huge number of blocks of large file will be distributed across multiple nodes. So first download the data node and install the data nodes in some of the computers in your lab. And then install a name node software. Name node will be installed in one of the computers. So choose one of the nodes has sufficient resources and install name node software. So your name node software basically maintains a file allocation table. So it will maintain the mapping of a particular file, how many blocks are there, in which of the data nodes the blocks are installed. All these mappings will be installed in the name node. So first thing, you have to choose some of the nodes in your lab, then install in each of the nodes, install the data node part, and then choose one of the node and install the name node. And now I will show how you can write your code to read and write a large number of HDFS. So next let us discuss about HDFS read operation. So let us assume that this is your Hadoop distributed file system. These are the data nodes and these are the blocks of the files available. And this is the name node where the metadata is installed. And this is your laptop or desktop where you are writing your client code. That want to read a large volume of files. The size of the file is such that it cannot be installed in one of the computers. So now let us see how we can write the code to read this large volume of file. So let me show you an example using a Java kind of thing. Suppose HDFS client is written in Java. So that can run in any of the computers. Even it can be run in a mobile phone also. That using a mobile phone, how you can read petabytes or exabytes of file. Right. So the first thing you need to do, you have to create a DFS object. So this is the things through which you can create a DFS object. When you create a DFS object, you have to pass a configuration. This configuration has the information about the name node, its IP address, its port, its user authentication, and all those things, so that it can have a connect to your name node and create a DFS object. Then you have to open a file. For opening a file object, you have to specify the name of the file, the path of the file. Once you get the path of the file, it creates this FS data input string. So this object will be created once you open by specifying a file name path. Once this FS input string is created, this is basically configured with some initial block information, because your file may have billions of blocks. So you do not read all the blocks. So it will return the first 5 or 10 blocks to your data input string. And then when you start reading in a loop, suppose this one you read in a continuous while loop, because the whole file is yours. You cannot read all the file at once. You can read one of the blocks. So how it read this? So it will use the first block information and go to the block, read it. Once this is complete, automatically go to the next data node and read the next block. And once all the initial blocks are completed and still you in the loop, you must still continue reading it. It will request the name node to return the next few block information and you continue reading this. And all this complex communication, inter-process communication between your clients, between the data node, among the data nodes and the name nodes, all these are working transparently. You do not need to write this inter-process communication, storage, reading, handling. Any file IO is not written by your client. You can see you just configure to get access to the name node, then open a file with the file path and then start reading in a loop. Each time you read, it will read one block information, that is 64 MB. Now using that, you will perform some processing on that data and continue reading as long as you want. So this is a stream kind of environment where you read it. Once you are done with your analysis, just close the same for that, and it's complete your read operation. Now, if you look at this code, it looks like that you are reading a file from your local computer, but at the back end, it is reading from a cluster of huge number of nodes, which is handled by this middleware called HDFS. So HDFS is a very good middleware platform to store a large volume of data. So that you have an IoT application, you have a machine learning applications that generate huge number of data that cannot be stored in a single computer. So in that case, this large volume of data, you have to write to the HDFS platform, and then anytime you can read it from any point of view, any subset and read it. Now let me show you how you can write it. So we read this part. Now let me discuss about how we can write the data. We have IoT devices. IoT devices generating the same data continuously, 24 hours a day, 7 days in a week, and continuously going on. And you do not want to lose the data. All the data you want to store it. So think about the data generated in 1 year. It's huge. So you cannot configure this kind of IoT platform using a centralized storage. So you have a distributed file system kind of thing, and through which you can write and later you can read it. So let me show you how we can write it. In the same way, your client needs to create a DFS object. Similarly, in the configuration, it will specify the specification of the name node, pass the configuration and generate your DFS object. Once you create the DFS object, now call the create function. So for reading, I call the open function. For writing, I will create the create function. Once you create, it will create your output stream object, data output FS data output stream object. Now, once you get your output stream object, just call write operation on that object. So using that, you just call write. So then you can write continuously the data. So when you call the write on the output stream basically requires the name node to allocate the block. So one thing you have to keep in mind that when it allocates the block, it allocates in multiple replicas because it provides a high availability. So that if one of the data node is down, the data is available in other data nodes. The default replica factor is 3. So that's why whenever you start writing for each of the block, it creates 3 replicas. And while it writes to the replica, it does not write one by one. It writes in a pipeline called write pipeline fashions. So the thing is that it writes to only one replica. Once the replica is completed, it is the duty of the data node to copy it to the second replica. Once this is done, it is the duty of the second data node to replicate to the third node. And once it acknowledges terms, it completes. So this is sometimes called eventual consistency. So initially, all the replicas become inconsistent. The first one is only consistent one. Once the second one is completed, the 2 becomes consistent. And once the third becomes completed, all the 3 replicas become consistent. So we call it the eventual consistency of HDFS operation. So I hope you understand that how we can have a middleware to store a large volume of data. So is there any question till now? Or otherwise I will continue to the next. So at any time if you have any query, you can ask. Any question till now? I just covered a distributed computing platform where we can store a large volume of data and later we can read it, and that too in a streaming fashion. So continuously data is coming. It's not that I have a file I have to write. It's not that there is a file I have to read. So it's a streaming kind of fashion. The data is also coming continuously and the analysis is also going on continuously. So in streaming fashion I can write and read using HDFS. Any question till now? Okay. So let me continue with the next one. So next, let me discuss about that I have a large scale storage. I store the data. Now I have to perform some analysis on that. So it can be a machine learning analysis, it can be some RV analytics or FRV analytics or any kind of analytics job on that. So for that, the platform or the middleware is called the map reduce. So let me show you how MapReduce can be used, how MapReduce middleware or MapReduce platform can be used to massively parallel coding for your analysis job. So for example, let me take an example of I want to calculate the frequency of the occurrence of each of the data. So suppose this is a large volume of data generated by your IoT devices or on any data set provided by your machine learning platform. And we want to calculate the frequency of occurrence of each of the data. So how we can do it? So we know that a simple algorithm to calculate the frequency of occurrence of each of the data is order of n square if there are n number of words, because we need 2 times scanning of the data itself. It's a simple. There is some better algorithm as well, but a simple one is that you will scan through reading each of the word 2 times, and you can find the number of occurrence of each of the data itself. So in general, there is an order of n square complexity to generate the frequency of the occurrence of each of the data. Now let me show you how we can use the MapReduce so that you can calculate the frequency of occurrence of each data in order of 1, not order of n. So order of n is very easy kind of things because you are reading, but order of 1 is interesting. That the time needed to calculate the frequency of occurrence of each of the data is independent of the number of words present, number of data present in that input. So let me show you how we can do that magic, that from order of n square we go to order of 1 using MapReduce kind of platform. So MapReduce has those many steps. The first thing is that suppose this is your data, first use HDFS write operation that I showed in the previous slide. Once you write the HDFS write operation, so that will create multiple blocks. Each of the blocks, suppose this is block 1, suppose this is block 1, and this is the 64 MB of the block. This is the content of that block. This is the second block, and this is the content of this second block, and this is the third block, and the content of this is this. So automatically your input data is divided into 3 blocks, each of them is 64 MB and distributed across multiple data nodes. So automatically your data is distributed using HDFS write operation. So this operation in MapReduce term is called as splitting. So we split your data across multiple nodes. If we use HDFS write operation, so basically they will be split across multiple data nodes in terms of the blocks. Now the second step is that we need a mapping function or map function. What a map function does? Map function takes a key value pair and generates a set of key value pair. So what is the input here for that map? The input is this block ID is the key and this block is the value. So each of the map function takes a block ID and the content of the block. For example, the first map takes 1 and this block. The second one takes 2 as the key and this is the block. The third one takes 3 as the key and this is the value. So each of them take a key value and it generates a set of key values here. What it does, it will read each of the block. So for each of the terms within the block, it generates one map. The term is the key and the value is 1. So once it reads, so beer becomes the key and the value becomes next beer becomes the key and value becomes 1. So this one is generated by this code. So this mapper function will take this block and generate this key value. So it takes one key, one value and generate a set of key value here. And that to run parallelly in all the data nodes. So if there are k number of data nodes, on average each of the map take in by k number of data. And since we have a single for loop, so its complexity is order of n by k. This is the complexity of this map function, order of n by k. If there are total n number of data and there are k number of data nodes. The next step is the suppling. The suppling is the distributed hash function. What it does, it takes the key of that map function, perform the hash, and the return value is the node ID or the data node ID where this has to be moved. So wherever the DR occurs, for example, DR1 occurs here, DR1 occurs also here. If you perform the hash function on the DR, they will return this node ID as the output of the hash function, and it moves the DR to that node. So automatically they will be shuffled. All the similar words will move to the same data node after this distributed hash function. And the time complexity of distributed hash function is order of 1. So I'm not going to prove that, but But we know that the hashing, if we have a perfect hashing, we can do it in a constant time. And the next is that the last part is a reducing function. So you need to write a reduce function. The reduce function basically take a key and a set of values. For example, for this one, the reduce take a key as beer and it take a set of value these two, 1 and 1. This one also take car as the key and the value as these three ones. So they take one key and a set of values. All the values associated to the same word, they become a set of values. And what it does, a set of key value here. So for generating this value, you simply perform the sum operation. So you basically add all these values and generate. So for example, the output is Day-2 because it performs the sum on this set of values. It also performs the sum of these values. So automatically it generates card 3, Day-2 and reverse. So that also you can see this is a linear operation. So the complexity of reduce function will be order of n by k. And finally you write it to be your HDFS. So now you can see the overall complexity is order of n by k because it will be additive. Frequency 1. Now if k equal to order of n, that is if we can provide sufficient resources, k is the number of data nodes. We have so many data nodes equal to the number of data. So now this becomes order of 1. So as you increase, the time complexity reduces. As you increase more resources, and once the number of resources provided for that computation is order of n, where n is the input data, your complexity becomes order of 1. So you can find the frequency of occurrence of each of the data in constant time. It's independent of how large the file is. So that is the beauty of MapReduce that we can use for different purposes. And this is a very key step to calculate the frequency of occurrence of each of the data in any of the machine learning operations. And that we can do it in constant time. Well, so with that, I covered the first part of my discussion, that how we can provide a middleware to store and analyze a large volume of data. In the second part, I will discuss about the middleware for large-scale computation. Not only storing the large volume of data and performing some analytics job on the data, but here any kind of computation. It can be a normal desktop application, it can be a railway reservation application, or any large-scale applications in a cluster environment. So for that, generally we use a cloud computing. So not the MapReduce kind of things, or not the kind of things. So let me now discuss about what a cloud computing platform provides for large-scale computation part. So again, the same data center we will use, but in each of the, on top of each of the web server, in cloud environment, we install the software called hypervisor or virtual machine monitor. What hypervisor does, based on the request from that user, each hypervisor can generate some virtual machine or can create some virtual machine and run on top of each of the web server. On top of each of the web server, you can run multiple virtual machines, and the job or the task or the processes of each of the users will be running in that virtual environment, not directly on the web server. So in the previous one, there is no concept of virtual machine. All these tasks are running directly on the web server to store or to perform analysis. But in cloud environment, what it does, using hypervisor, it creates virtual machine. This virtual machine can be easily created and destroyed whenever they need, and you will run it. So based on that platform, it provides some features to you to be helpful for large-scale computation. The first is that they provide on-demand self-service. On-demand means you do not need a server beforehand. Whenever you need, you send a request, it will launch a virtual machine for you and run your job. And once you are done, terminate this virtual machine. So the resources of the web server is again retained. So that's why this is called on-demand and self-service. Just you send the API request to create a virtual machine. So no one required to create your virtual machine. You will send the API call, it will create a virtual machine, place in one of the web server and give access to you. You use it, once it is done, you terminate your machine. So no one is there. That's why this is called a self-service kind of nature. And whenever you need, so that's why it is called on-demand self-service features of the cloud environment. Second thing is the broad network access. You do not need a very high-speed network connectivity. Even from a mobile phone also, you can create a virtual machine and use it. So from a broad network access, you can access this cloud services. Next is major service. So based on the virtual resources you use and how much resources you consume, you have to pay for that. And that creates your multi-tenancy environment kind of things. So the same resource is tenanted by multiple users, and they are using this in a round robin fashion. So as if everyone is considering the great server in itself. So they have to pay a very low cost since this is a multi-tenancy platform. So at a very lower cost, you can have access to a very large scale computational environment and the rapid elasticity. So you can launch or increase the number of virtual machines very quickly. Within a minute, you can launch billions of virtual machines, and within a minute, you can terminate all the virtual machines within a minute. So very quickly, you can increase your amount of virtual resources, or you can decrease the amount of virtual resources. So that can be used for effective resource management in cloud environment. So this feature is called rapid elasticity. And all these characteristics comes at the cost of some issues. The first issue is basically latency. So you have to send your job to the data center, and once the computation is done, the result has to be downloaded. So automatically it increases the latency of your computation. The time required increase. Second is the security. Obviously, your data is stored or task is computation in a third party. So you have a security issue involved here. And the third one is the vendor lock-in. So you have to pay money for using that. Now you write your application using the API of one of the vendors, and you want to move to others, but the API does not support. So you may be locked in one of the vendors. So these kind of issues are there, which is not in traditional environment. But anyway, the features provided by cloud outperforms the issues there. So that's why everyone and every service now put it towards the cloud environment. So I hope this one you already know, I just covered it. Now let me discuss about one feature that is also nowadays using along with the virtual machines. These are called the unikernels. The unikernels is like that. In a virtual machine, instead of creating a virtual machine for all the services, since we get the microservices, for each of the tasks, we need only one service. For example, suppose this is a task for in the INX service we need. So for that running that service, we do not need lots of data. For example, you can see we have a kernel on top of web services, then there are lots of libraries, and there are some third-party applications are there. So for NGS, you can see for each of the layer, we only need some subset of services. But if you use a traditional virtual machine, it will have all the services which are unused. But if you go for microkernel, you can create your kernel, you can create your OS using only the service required for each of the layer, and you can create your virtual machine intact with your application as well as the web services. Now, what the advantage we get with that? Obviously, since we removed most of the unused services from each of the layer, the total, your application and operating system, the total size comes to some kilobytes. So it's very low size. So it is very fast to boot. The time required to start your service is very less. And since each of the virtual machines run only one service, there is no context switch inside the virtual machine. And we know that the context switch has lots of overhead. So this context switching overhead is removed while you run your service inside your virtual machine. And it can run on hypervisor, container, or bare metal, or lots of layers. So this virtual machine can be run directly on a bare metal instance or on your desktop itself. Since the OS and all the services needed are packed in your virtual machine, it does not depend on the services running in your computer. And third, most important thing is the small attack surface. Since most of the services are remote, a virus cannot directly attack it. Because if a virus is running in a virtual machine, they may need some of the services which is missing. So virus will not work. So the attack surface reduces drastically. So nowadays we are going to use the virtual machine with unikernel for running microservices for distributed computing platform. So with that, let me show you a practical example of using the cloud services. And the most popular one is the AWS or Amazon Web Service. So in Amazon Web Service, each data center, the term is an availability zone. So already I told you, a data center is a collection of racks with some web server. So in AWS, the term is as availability zone. Now, within a particular region, for example, in the Europe, they have lots of data centers. So those data centers are connected by high-speed lease line connection. So this collection of data centers, they call it a region. And across the globe, they have lots of regions. And those regions are connected over the traditional public network, internet. And there is some lots of region across the globe. These are old statistics. So basically in US, Europe and in India also we have some data centers supported by AWS. Now this AWS, if as a user you want to use, there are three options. Either you can use some command line tools to access the AWS data centers for running your large scale job analytics, or there is some SDK where you can directly write, you can code it, all the APIs that can be coded into your SDK platform and you write coding directly there. Not only the command line from your Eclipse environment or your programming environment or your Python environment, you can directly import it. And the execution of your Python code or the Java code can directly impact on the data center virtual machine. Or you can go to their website. Through that you can launch a virtual machine, log in here and you can do it. So these are the three options to use Amazon Web Services. Now let me show you what are the services provided by Amazon. The various infrastructure services provided by Amazon are mainly three important services: EC2, Elastic Compute Cloud, EBS for storage, Elastic Block Storage, and S3 for large scale backend storage. Simple service. So let me show you how we can use it. Suppose you launch some virtual machine in Amazon data center. Suppose virtual machine 1, virtual machine 2. So these two virtual machines you run using the EC2 service. And then using EBS service you launch EBS or block storage. So EBS is something like a pen drive kind of things. A block storage that can be mounted dynamically to any of the virtual machines. So using EC2 you launch two virtual machines. Using EPS service, you create a block storage for example, 5 GB or 10 GB block storage you create it, and then you mount it. So since they are mountable, you can mount it to either VM1 or VM2. The only requirement is that this VM and the EBS should run in the same region. Otherwise, it cannot be mounted. So now suppose you mount it to the VM1, you run it, and later if you want, you can unmount and mount to the VM2. So the data exchange between these two, you do not need to transfer. So usually the output of VM1 can be read by VM2 without transferring the data from VM1 to VM2. So that way you can use the EBS along with the VM. Later if you want, you can create some snapshot from the EBS. So snapshot are basically a zipped version of the content of the snapshot. And from that snapshot you can create as many EBS you want. Again, that will create an unzipped version of the block storage, and those EBS can be separately mounted and work on parallelly. So using the EBS and snapshot they provided by this EBS service, you can have lots of applications you can design. But these EBS are directly connected to your VM. So they cannot be used as large scale storage for archival data. For archival data, there is a S3 storage. So in the S3 you can have terabytes or some petabytes kind of data, huge amount, and that can be downloaded. So this S3 storage cannot be mounted. If you want to use, you have to download it to the in storage of the VM or to the EBS and perform the operation. And the backend archival data, you can load it back to your S3. So that way you can use the various infrastructure service provided by AWS. Another is the V2C. For security purpose, you can create a virtual private cloud so that the data communication among S3, VM, and EBS will be encrypted. So you do not have the fear of data theft or data loss kind of things. Now let me show you some platform service also. Amazon also, AWS also provides some platform service. Let me show you some platform service for your large scale data and analytics. So for that they provide these three services: RDS, DynamoDB, and EMR. This RDS is basically nothing but your MySQL cluster. It can be a MySQL cluster, it can be a Oracle cluster, it can be a SQL Server cluster itself. So if you want a large scale MySQL cluster, just use RDS services. AWS will provide you a cluster of nodes, and that can provide you your SQL query on the large cluster of MySQL engine, MySQL Oracle or SQL Server engine. And if you want a NoSQL kind of database, so for that you can use a DynamoDB. So if you have a unstructured data or semi-structured data, so don't go for RDS. You have to use a DynamoDB, where you can run your NoSQL kind of database services here. And if you want to Hadoop, whatever I discussed in the first part, Hadoop, HDFS, and Hadoop MapReduce. So for that, you can also use Amazon services called EMR, Elastic MapReduce. So for your Hadoop implementation in AWS, just use EMR. You do not need to install data node, name node, your write operation, read operation. Everything can be provided by EMR service provided by AWS platform service. Now let me show you one example or use case where we can use this EC2, S3 and UMR in a pipeline. So there is a AWS data pipeline kind of thing. Suppose there is a EC2 for each of the big data storage. So, or suppose there is a big basket or there is a big buzzer or lots of storage services are there. So their transaction they store using the virtual machine. And at the end of the day, they put it into a S3 about all the sale or all the transaction done on that the big bazar trade, big bazar point, and they store it in the S3. And at the end of the week, so there are lots of big bazar across India or across the globe. Everyone storing to S3, and this archival data I want to analyze. So what you need at the end of the week, using the UMR service, you create it, read it, and using map videos in a massively parallel fashion, apart from the analytics job, you can do it. And that one can be done in a pipeline. Automatically this data you can do, and your analysis is going on in a streaming kind of fashion. So this kind of platform you can also use for your big data analytics on top of AWS cloud environment. And some management services are also there. For example, CloudWatch. CloudWatch means suppose you are running your virtual machine and you want to monitor the health status of the virtual machine running in AWS. And once they are overloaded, you want a controller to add some virtual machine or remove some virtual machine. So this can be done by Amazon CloudWatch and Beanstalk. So CloudWatch is basically the implementation of the monitor that can monitor the virtual machine running in AWS, and Beanstalk is the controller. So in Beanstalk you can specify if the load of the average load of the VMs is more than 90%, add some virtual machine. Or you can add the rule to Beanstalk that if the average load is below 30%, then delete some of the virtual machine. So that kind of scaling can be done using CloudWatch and Beanstalk provided by Amazon. And if you want a messaging kind of service, for example, your WhatsApp or your SMS or MMS kind of things, you can use SQS and SNS. So SQS is basically for one point-to-point communication. For example, you have a WhatsApp client, you want to send your to friend. And for WhatsApp group or a group communication, you can use a topic. So topics are basically implemented by SMS, and queue is implemented by SQS. So using your queue and topic, you can use this SQS and SNS for implementing the messaging kind of service across your distributed computing platform. Okay, so this is the completion of my second part. So I'll be happy if you have some query we can discuss. Otherwise, I continuously talking and there is no query or no discussion. Any query till now?
Sir, I think no query.
Okay.
So please, sir, continue, sir.
So cover two parts. In the first part I covered a distributed computing platform for large-scale storage and large-scale analysis. And in the second part of my discussion, I discussed about large-scale computation using cloud. And I showed one example that what are the services provided by AWS, Amazon Cloud, which is the most popular one to use the cloud services, and how we can use it for solving different kinds of problems. In the last part today, I will discuss about some of my research work that is going on to how you can schedule the resources for your big data storage or your cloud platform. So we call it a resource scheduling strategy, how we can use it. So let me discuss about in terms of the cloud platform, how we can schedule the resources in cloud. Already I show you in a cloud platform we have lots of base server, and on top of the base server there is some hypervisor, and that allows you to launch the virtual machine in base server. So obviously one research problem is how can you place the virtual machine? You have a lots of hosts, you have a lots of base server, and there is a lots of requests for virtual machine. Now each base server should run the virtual machine. So that mapping is called a virtual machine placement problem. So VM placement problem is an important resource scheduling problem in cloud environment. Another thing is that if the VM placement decision was not right, later we may need to migrate some of the virtual machine from one base server to the other. So that is called game migration problem. So that balance the load, that also may be beneficial from energy consideration or other part. So broadly, the resource scheduling in cloud are divided into these two parts: game placement problem and game migration problem. So initially you have a request for VMs, set of VMs are requested, and you have a set of hosts of web server. How can you map it? How can you place the virtual machine into the host? So that is the game placement problem. And on the runtime, if you want to migrate some virtual machine, how you can choose the victim virtual machine? Which virtual machine has to be migrated and where to migrate? So this is called a VM migration problem. So first let me discuss about the VM placement problem. So we can consider this VM placement problem by mapping it to some rectangular box placement kind of things. Suppose these are the blade server, we call it physical machine. This is the one physical machine, this is another physical machine. Each are the blocks, each are the blade server in the racks. Now, if I consider only two metrics, because these are the two metrics important for running any task: how much CPU you need and how much storage or RAM in memory you need. Apart from that, there is also a network or bandwidth you require, the backend storage you require, so lots of things are there. If I consider only these two important parameters, the CPU and the RAM, and if we can normalize the CPU and RAM, each of the blade server can be represented by a large rectangular box. So suppose the CPU requirement is normalized. So the value of CPU will be between 0 and 1. The value of the RAM after normalization will be 0 and 1. So based on the available CPU, based on the available RAM, this can be represented by a rectangular box. Similarly, each of the virtual machine requests also requires some virtual CPU and virtual RAM. So they can also be represented as a rectangular box after normalizing their requirement. So obviously, this VM box will be very small box and the base server box will be large box. So the requirement becomes that how optimally I can pack this virtual machine, these boxes inside the large box. So optimally how can do it? So we can find some IP to solve it. For example, we can have a decision variable because we don't know which mapping is optimal. So we can have a decision variable xik. So this xik will be 1 if the ith virtual machine is placed on kth physical machine and 0 otherwise. And UK is another variable. This is not a decision variable, this is a mark variable, that this will be 1 if at least one VM is placed in a PK. So we have to see if UK equal to 0 means none of the VM is placed into that physical machine and this physical machine will be turned down. And if UK is 1, that means at least one of the VM is running placed in that physical machine and that has to be continue running with there. Now our objective is to minimize the sum of the UK. That how we can run those games with minimum number of physical machines. So since UK equal to 0 or 1, so this will be minimized means the minimum number of physical machines will be used to run those games, to solve your game. Now there is some constant. What are the constants? The first constant is that the sum of the total memory requirement. If a virtual machine is placed in a physical machine and the virtual machine has this much memory requirement, this total sum should not be less than, this should be less than the available memory. Similarly, the total CPU of all the VMs running in the physical machine should not exceed the capacity of CPU on the physical machine. And the next one is that a virtual machine cannot be placed across multiple hosts. So if a virtual machine is placed in one of the physical machines, in other virtual machine, other hosts, it will not be placed. So the sum of all the x variable will be 1. And since this is 0 and 1, this is 0 and 1, so it says that a virtual machine is placed at most one of the physical hosts, not more than that. And the UK should be greater than xik. That is, if xik is 1, UK cannot be 0. So UK has to be more than this. But if this is 0, UK will be automatically set to 0. And all the variables are there. So ultimately, if you solve this objective function based on this constant, it will provide you the optimal solution. But we know that this IPK, this solution is not a polynomial. So this is basically a empty-hard problem. So what we can do, we can use the simple 2D bin packing problem heuristics so that we can solve in reasonable time. And we know that the various heuristics for bin packing problem in the two-dimensional space are best fit, first fit, best fit, and the worst fit. So these are the traditional, and we can find the approximation ratio that they approach to the optimal one. But what happens if we consider the hard disk, if we consider the network bandwidth, so automatically it becomes the multi-dimension. Instead of 2 dimension, it becomes multi-dimension 0-1 bin packing problem. So this fast fit, base fit, or the host fit can be just slightly modified to cope up with the multi-dimension itself. So we can use it. Now, if we consider the energy, so not only this kind of packing, the minimum number of physical machines, it may be that all the VMs are running with minimum number of physical machines, but the total energy requirement may be much higher. So we modify the base fit decreasing. This base fit, we find the base fit is the best algorithm to bin packing, and that is modified to consider the energy efficiency. Our objective is not to minimize the total number of physical machines. Our objective is to minimize the total number of energy, because this energy requires your electricity bill. The total bill at the end of the month for your data center based on the total energy consumed. It's not how many physical machines are running. So we have to modify the base fit decreasing to consider the energy, not the number of physical machines running there. So this modification is very simple, that once a request for VM comes, suppose this is the VM request come, so we have to look for all the hosts, all the blade server available, and we have to estimate the power. So this power estimation is important thing, that if we launch this VM to that host, how much power is required, and that you have to do before running it. So that's why we have to estimate it. We cannot exactly calculate how much energy is completed. So we need an energy estimation for running a VM in a particular blade server. And the best fit is that the host where this power, estimation power is the minimum, it is the best fit. So using that, we can modify this best fit decreasing, and we can find better solutions towards the VM placement problem, considering the energy. Now, the thing is that how can we estimate this power? So for that, we need some power modeling. So let me show you what are the various power modelings you can use for your estimation. So what we done is that we have some server to test how much power for your varying workloads. So first, choose your server, add this power meter to your server, and then vary your workloads. Increase the CPU load, increase the RAM, or lots of benchmark data are also available there. If you run it, lots of combination of the benchmark data will be there, and it will generate how much power consumed by this kind of workload. So after pre-processing, you can perform the model training. You can create a power estimation model, and this model can be used to estimate the power for running a VM in a host. In general, the power models can be, this power can be modeled either linearly or non-linearly. So accordingly, we have some linear power models and some non-linear power models. Now, each of the linear and non-linear power models can be modeled either mathematically or using machine learning. So I will show you that how mathematically you can model a linear power model or non-linear model. Also using machine learning, how you can model the power using linear and non-linear. So for machine learning with linear, you can use single variable linear regression or multivariable linear regression or lasso regression. So all these three will provide you linear power modeling based on the machine learning. And for non-linear machine learning, we can use a single variable polynomial regression or artificial neural network. So ANN you can use for non-linear version of the modeling of the using machine learning part. So let me now show you how this can be used. First, let me discuss about this mathematical modeling of your power estimation for energy. So for the first one, you can see for the linear model, so you can use this kind of things. The power estimated for the load, CPU load of U is the usage. If we have a CPU usage, how much power is needed? So that can be modeled by this kind of mathematical model. You can look at this. The model is Pmax minus Pmin into the CPU utilization plus Pmin. What is Pmax? It is the maximum power. That is when utilization is 1, what is the power? That is called Pmax. And Pmin is the ideal power. When utilization is 0, what is the power? Now you can see when this utilization is 0, the power is Pmin. And when this utilization is 1, this Pmin cancel, this is Pmax. Now, if you provide a utilization in between 0 and 1, this linear model will give you an estimate of the power for that particular CPU usage. So this is a mathematical model. I do not need a machine learning or something to train it. Mathematically, I can use it if the corresponding machine follow a linear power model. So that can be simplified to make it this kind of things. For example, we can use this kind of constant, this 70%, 30% kind of rule. So only one parameter can be used. But this is the main part. This is the mathematical model, linear model to estimate the power. That if we put a host, we know the host how much utilization can be generated, then how much power will be generated in that host. So different blade server has different kind of parameter. This Pmax and Pmin will vary from one blade server to the other. So obviously, if you place a virtual machine in one blade server compared to the others, their power estimation will not be same. And we have to choose the best thing, where the estimated power is minimum. Another is nonlinear. So nonlinear has lots of models. This is one nonlinear model. So instead of just multiplying U utilization, we can have this kind of model. It is a single parameter, 2 times UCPU minus UCPU utilization of the CPU to the power R. This is another example where you can use two parameter alpha and beta, and you have to model it. Or you can use the piecewise linear. So for example, you can calculate the power P1 for the utilization CPU1, and you have to calculate P2 for the utilization U2. Then you can use this kind of piecewise linear regression that for a particular U, from these parameters you can generate this thing. So obviously this is non-linear. So this kind of mathematical model we can estimate the power, and once you estimate the power, since the utilization varies over time, you can perform the integration of all this estimated power and find the total energy required. And how can you perform that integration? Because this function is basically continuous. So what you can do, you can perform the piecewise breakup. So we can have this, and instead of this, you can perform the summation. You can perform the discrete sum of this value. So you may not need to perform the integration of these continuous values here. Now let me discuss about the linear regression model. So let me discuss about the machine learning part. So first I will discuss the machine learning modeling for linear, then I will discuss about the machine learning modeling for non-linear. So the first one is the linear regression model. In linear regression model, we have only two parameters, alpha and beta. So the power estimation will be alpha plus beta into UCPU. So based on that, you can estimate alpha and beta, and you can use it using a single linear regression kind of fashion. So you can see this alpha will be your P-mean most of the time, because when utilization is 0, the alpha is basically P-mean. So basically we need to estimate only beta, not the others. Now, if there is multiple variables, that not only CPU, we can have a CPU utilization, we can have a memory utilization, we can have a bandwidth utilization, so lots of variables are there. So in that case, this simple single variable regression will not work. So we need a multi-variable linear regression. So this is, we know the standard fashion, standard equation for that multi-variable linear regression. So suppose this is the power for this particular use case, and for that estimation, this is the error term. And we need to estimate this so that the mean square error will be minimized. So ultimately, our objective is to find this beta vector, the beta 0, beta 1, beta 2, this beta vector, so that it minimizes the sum of the square of the errors. So yi minus beta 0 minus the sum, this is the error and its square, and that has to be minimized for which beta. So that will give you the solution of the better model using machine learning. But sometimes the overfitting problem occurs, that some of the parameters we want to reduce it. So that can be performed using lasso linear regression. The lasso linear regression is the same thing, but it adds this part with the weight. So since we want to minimize this, and we try to minimize, we try to force some of the beta to 0 so that its size reduce. So the parameters which are not so much important, they will be automatically set to 0 by this part. So if you use lasso regression, so it will provide you much accurate model to your power estimation. Now let me discuss about the machine learning for non-linear models. So if this is non-linear, we can use the neural network kind of things. So the neural network kind of things means for all the servers you have lots of performance data. From the data you can create this performance data for different usage. What is the power? So based on that power, you can give you the input layer. Then you can have a hidden layer using a ReLU function, and finally a linear of all the output of the ReLU to give you the estimation. So it's very simple. The hidden layer can be performed using that ReLU, and the next layer is a simple linear combination of that. So using this kind of neural network, you can also model if it follows nonlinear pattern of your power estimation. And you can also use iterative pattern. So Illman neural network kind of things you can also use. So not only one hidden layer, it can be multiple hidden layers. So iteratively, the output of the first will be moved to the second and continuously in an iterative fashion. So this can work, and finally you can get the result there. So for each of them, you can define your own activation function, and finally the last one is always linear combination. So these kind of things you can use for modeling your power estimation. And the last one that I want to discuss is that in the previous one we read the data and then you model it. So sometimes we need to predict what may be the future load. Previously I do not know the load. So based on the predicted future load, we want to model it. So for that, we can also use a Markov chain based prediction. So suppose these are the states. Markov chains, you know that there are lots of states, and based on that, you have to predict what are the next states. So for example, suppose these are the states for CPU utilization. I want to predict what will be the CPU utilization ladder. So for example, suppose based on if the CPU utilization 0 to 10%, this is state 1. If it is 10 to 20%, this is state 2. So 20 to 30% state 3 kind of things. So based on the variation of the CPU load, we can represent these as a state. For example, at T1, it is state 1, state 2, state 3, again state 3. That is CPU load increase, then CPU load decrease, again CPU load increase, kind of thing. So the reading of the CPU loads across a time can be represented as a time series of the state. And we want to predict what will be the future load going on there. Now, in Markov chain, what it does, from that observation, we can represent the state transition matrix. So from there, you can see from S1 there is a transition to S2. There is from S1 there is a transition to S3. So from that you can find from S1 what is the probability to go to S2. From S1 what is the probability to go to S3. So from that history data we can easily calculate this probability, and you can get a transition probability matrix. Once you have done this, from there you can, so basically from this transition diagram you can get this transition matrix, and then Markov chain says that we can use this kind of chain of this to predict what will be the future. So for example, what is this first one? The first one is, you can see the last state is S3. So that means this is your phi 1. Phi 1 is one row. And in the phi 1 you can see the highest value is 1 by 2. So you predict S1. That is. And how can you do that? The next prediction. So you have to, this row has to be multiplied with this. And you can find what is the highest value in S1. So gradually you can find S2, S3, like these things. So you can predict those future utilization, and based on the future utilization, you can apply to these models, one of the models, because in the input you have to give this utilization. So instead of raw utilization, you can input the predicted utilization, you can predict the model power estimation, and based on that run it. So that will reduce your migration time, because previously you know where it is best suited. The first one, without prediction, it is installed, it is placed, and over the time it sees that this is not good one, so migrate it. And in prediction, we predicted and see where is the best one, and just place it there. So it does not require any migration to other part here. So I think with that I covered most of the part. If required, I can continue, or otherwise I can stop it here, because I know in an online mode continuing 2 hours is too tough. So if required, I can continue with that broker part, whatever you need. Otherwise, I can stop it here itself. Momentarily. question, or if required, I can continue to the other part. Hello, am I audible?
Yes, sir.
Yes. So I want your feedback that whatever I want to cover, I cover it here. If required, I can continue some discussion on my other research. Otherwise, I can stop it here. And if you have some query on that discussion, we can continue that discussion.
Uh, Sir, am I audible, sir?
Yeah.
Sir, can you please repeat once?
So
Actually, your voice was slightly cracking.
yeah, I just said that with that I can complete and continue if you have any discussion, if you have any question.
Oh, okay, sir. Got it. Dear participants, you are requested to put your question in the chat box if you have any query. If any participant have any query, please put your query in the chat box.
Yes, there is a question for you.
Uh, Deepa, you are requested to put your query in the chat box, please. Sir, I guess there is no question from any participant.
Because Deepa has raised her hand.
Yes. Actually, she has raised her hand, but I can see it raised down.
So should I complete it here, or I have to continue with the next discussion? Because we have 2 hours, but I think discussing so many things will be overloaded. So that's why I want to stop here and ask any discussion on the question.
Yes, sir. The question answer session will be more applicable, sir.
Yeah.
But I guess there is no question from any participant.
Okay. So I think it's here my mail ID. If any query is there, they can also send me a mail. And
Sir, can you please give your mail in the chat box, please, so that if any contestant have any questions, they can ask you directly in the mail.
this is my mail ID. So you can also mail me.
Thank you so much, sir, for sharing your knowledge with us. It was indeed a great pleasure to have you with us today.
Thank you.
So, yeah, yes, sir. It was a great pleasure to have you with us today. So with this, we will conclude here the first morning session of the FDP, and we'll just take a lunch break. And after that, we will be returning back by 3 p.m. for our second session.